So I wanted to make a comment about our final steps in the proof of the implicit function theorem. We wanted to work out the derivative of x, our function x here, and so we wrote x as a composition. And we needed to know a lot of things, actually, in order to get things to work. Not just using the chain rule to work with the derivative of a composition, but we also needed to understand how our function big F was related to little f, and how the derivatives were related. So we went and we tried to write everything down in terms of compositions and mappings to whatever extent we could. And then we were able to use the chain rule to turn all of our statements about functions to statements about derivatives of those functions. So all of our messy statements about functions turned into nice, clean statements about linear maps, where we could apply linear algebra ideas to make arguments. And the point that I want to make is that this is kind of a general principle. So, okay, so I did look, after I finished the recording of the last video, I looked at the length, and that was a really long video. So while I admit that that was really long, it is still much simpler than the stuff we did before, right? Like, if you look at what we had to do before in our proof of the implicit function theorem, we were staring at components of this matrix here, trying to invert this function here, chasing elements around. It was all actually pretty complicated. And compared to this stuff, like while this took a while to go through, partly because I got stuck in a certain spot and had to go back, and partly because it's notationally involved, still, what we did here was really actually very simple, right? It was just working with compositions, applying the chain rule, and everything involved in the end was linear maps and linear algebra, just composing projections and embeddings and things like that. So it was conceptually simple, even though it was notationally complicated. And I want to make the point that this is a kind of a general principle. So I made this drawing here. And if there's one thing that you come away with in 118A, B, and C, then I would hope that it's this. So on the left side here, I've got this cloud, which represents the world of things you study in analysis. So maybe differentiable functions, or maybe C1 functions, or whatever. So this is the world of things whose derivatives you take, things you study in analysis, functions like f of x. And then on the right side, I've got here this sort of clean, rigid world of linear algebra, vector spaces, linear maps, things like f prime of x. And differentiation is a tool that takes you from this world into this world. It takes you from this messy world into this nice, clean world. And it doesn't just turn objects from here into objects over here. It actually it does this in a way that preserves composition of mappings. So it doesn't. Yeah, so this arrow basically operates in the best way possible. What I'm trying to show you is a kind of category theoretical way of thinking. On the left side, you've got the world of differentiable functions, and on the right side, you've got the world of linear maps. And differentiation is what in category theory you might refer to as a functor from this messy world into this clean world. And thanks to the chain rule, basically the statement of the chain rule is that this transition from messy to clean over here preserves composition. So it preserves many kinds of statements that you make here. If you can turn whatever statement you're trying to make into something that involves composition, or that's written purely in terms of compositions and mappings, then it will be preserved along this transition. And this is a way of thinking about how to solve problems. This is a way of thinking in analysis and in mathematics overall, is that if you can find a way to turn messy, complicated things into nice, simple things, then you can turn messy, complicated problems into nice, simple problems and then solve them over here in the nice, simple world. And yeah, so I'm also hoping that this gives you some perspective on the importance of the inverse function theorem. So the inverse function, okay, so if you've got invertible functions over here, then just thanks to the chain rule, we know that they will become invertible linear maps over here. If you're using this arrow of differentiation to take problems, messy problems from here and turn them into simple problems and then solve your simple problems here, then how can you go back and turn your statements about derivatives back into statements about the messy things that you started with? You need a way to kind of go back and turn statements here into statements there in order for this arrow to be a reasonable way of solving messy problems. That is one of the things that the inverse function theorem does. It makes this arrow really much, much more powerful as a tool for solving problems by saying if you have an invertible linear map, then that can, on this end, then that tells you something about where it came from. It gives you some kind of invertibility statement about where it came from. So that and basically anything that, like the implicit function theorem is also that too. Anything that tells you how to get information, how to transfer information back from here back to over there is going to be really powerful and useful because it makes this arrow of differentiation be a very useful tool for solving messy problems by turning them into simple ones. Okay, and that's it for that. So, and that's it for 118A, B, and C for that line of development up to a certain point. Of course, there's much more to 118C, but I think we kind of reached a stopping point for that sequence, for that course. You know, the inverse function theorem and the implicit function theorem are sort of the two big things that you have to get to in a 118 course. And while there's more to Rudin Chapter 9, I think we've reached a pretty good stopping point for Rudin. So next time we'll, I guess next week, since this ran so long, we'll start with something else, which I will discuss with you guys once I figure out what it is.